Hello, everybody. So, in this video, we're going to continue the topic that we started a couple of videos before about the energy equation for the dynamic fluids. The equation that we're going to discuss here is a very, 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 very famous equation in fluid mechanics, which is called Bernoulli equation. And Bernoulli equation is an approximate relation between pressure, velocity, and elevation, which are the three forms of the mechanical energy that we discussed before. The equation has or is based on some assumptions. First, on steady flow, so it has to be or there has to be no change of any property with time. For incompressible flow, meaning that the density is constant and the friction forces are negligible. I'm going to discuss this a little bit here, and we're going to go into more details in chapter 8. We're going to cover this point in very, very deep details. The For any flow, internal flow, meaning that flow in a pipe or in a tube or any closed container or conduit, the fluid will while it's moving, it will be passing by the side. So there will be friction forces between the fluid and the sides, the internal walls of the container or the pipe, besides the friction forces between the layers of the fluid themselves. So all these friction forces are going to reduce the energy of the fluid. And this is something that we cannot avoid. It's something that has to be there. And these are due to mainly the property of the fluid that causes these friction forces in the viscosity, as we discussed in chapter 3 or chapter 2. I'm sorry. So the Bernoulli equation assumes that these friction forces are negligible, meaning that there is no viscosity effects on the flow, which we call an inviscid flow. So inviscid flow means that we ignore the viscosity effects. So this is what we mean by the negligible friction forces. Of course, this is not very accurate, and we're going to discuss how we can make the equation more accurate later. But this is the assumption that Bernoulli equation is based on. So these are things that we need to keep in mind before we go through the derivation. There is one more thing. It's a mathematical thing, more of a mathematical thing that we want to I want to cover here before we go through the derivation, because it's going to be one of the steps that we are going to go through in the derivation. So it's better to get it clarified here before we do this inside or through the derivation. So let's say that we have a steady flow in a pipe like what we see here. So steady flow, that there is no change with time. The pipe has a big diameter d1, and then gradually decreases until it reaches the final diameter, which is d2. We know from the continuity equation in case of steady state that if we have or we apply the continuity equation between a point here and a point here, then the mass flow rate is going to be the same. The density is the same. We assume it's an incompressible fluid. So the multiplication of U and V and A, I'm sorry, UA is equal to UA here. And since the area here is smaller, then the velocity here is larger. So U2 is larger than U1. So through this gradual decrease in the area, there is an acceleration, meaning that the velocity increases. But the velocity doesn't increase with time. The velocity increases with distance, with S. It's not with time, meaning that if I pick a specific point here and I measure the velocity now, and after 1 hour or after 1 day, the velocity is going to be the same. So there is no change with time. The velocity changes with distance. So this is the acceleration is due to the change of the distance, not the change of time. And that's why we need to express the acceleration in a way that takes into account the or that is not du by dt. It has to be something else. So it's a mathematical trick. It's a very simple mathematical tweak here, that we know that there is the acceleration is du by dt, and there is a rule in differentiation. It's called the chain rule. So if we have du by dt, it's equal to du by ds multiplied by ds by dt. This is the chain rule. So the chain rule can be used in this case, and we can rewrite this equation as ds by dt is the velocity, and du by ds is du by ds. So the acceleration can be expressed as u du by ds. So this is just another way of writing the acceleration. Okay. Okay. So now let's go through the derivation of Bernoulli equation. So Bernoulli equation, as we do all the time, we are going to have a differential volume. In this case, it's a cylindrical element like this, and this cylindrical element has a distance or a length of ds and a cross-section area of dA. And this differential area is or volume is this is the side view of this differential volume. So this is the same thing, but from the side, and it's going in non-linear path at a random angle. So to make this general form or a general equation, and these are the coordinates z and x, or z and x. The z is the vertical, x is the horizontal. The gravity is acting on the negative z direction, so this is the weight is acting downwards. And there are some forces that we can see acting on this differential volume. First is the pressure is causing a force from this side, and there is pressure plus dP acting on the other side. So it's PdA, this is the force, this is P plus dPdA, the force on the other side. And there is the weight, which is acting downward at an angle theta to the normal to the axis of the differential volume. So anyway, so this is what we have here. So the derivation is simple. It depends on the very well-known Newton's second law that states that the summation of forces equals mass times the acceleration. We put here a subscript s for the F and A to show that this is in the S direction, meaning that along this streamline. And by the way, the streamline is the line that the fluid is flowing through. So you can think of it as a path that the fluid is going through. So the forces, what we are going to, again, we have here in this case, we ignore the friction forces, we ignore the pumps and turbines, so there is no mechanical force, mechanical work from outside. So the summation of forces is the pressures, the weight, that's it. So you have P dA minus P plus dP dA. Of course, we are having this as the positive S direction. So anything acting on the opposite side is going to have a negative sign. That's why you put negative sign here, P plus dP dA minus W sine theta. For the W will have two components. One in the n direction, which is the normal to the streamline, and one which is on the streamline. So this normal is going to be W cosine theta, and it's not of interest for us. What we are interested in is the one in this direction, which is negative W sine theta, which we have here. Okay, and if we look at this, it's already here, but I think you might not feel how this relates to this. So I tried to draw it in a more detailed, a little bit detailed. So this is the normal, and this is the weight acting downward. This is angle theta. This is ds. So ds can be considered as a hypotenuse of a right angle triangle. The vertical side is dz, and the horizontal side is dx, because this is parallel to x-axis, this is parallel to z-axis. So this angle theta makes a right angle with this angle here, and this angle and this angle both make 90 degrees angle. So this is common. This plus this is 90, this plus this is 90, so these two are equal. So this is theta, which is the same angle as this, and sine theta is dz or dz by ds. Okay, so we can write sine theta as dz by s, and we can simplify the equation. So this p will cancel this negative p, so these two will cancel out. So you'll end up with negative dp dA. The w is mg, m is rho v, so it's rho dv. So it's rho dA ds. This is the mass times g. Sine theta is equal to rho dVAS, and dV is dAds. So it's rho dAds is the same as rho dAds, the same m. Okay. The difference here is the acceleration, which we put as u du by ds. Now we can simplify the equation by putting sine theta as dz by ds, and now this is the equation. We can simplify the equation by multiplying the or dividing of course this ds will cancel this ds, so these two will cancel out. So we can divide the whole equation by dA, which is present in the three terms, and by rho. So if we divide by rho dA, this is the equation that we will have: dp over rho plus g dz plus u du equals 0. These are all differential terms that we can integrate, and the integration will yield the very, very, very famous Bernoulli equation, which states that p over rho plus gz plus u square over 2 equals constant, okay, which is a conservation of energy equation. Now we can express the equation as the sum of kinetic, potential, and flow energies of a fluid particle is constant along a streamline during steady flow, which is the assumption that we made, and when compressibility and friction effects are negligible, which means that it's an incompressible flow and inviscid flow. How this relates to the equation: P over rho represents the flow work, Gz represents the potential energy, U square over 2 represents the kinetic energy. I'm going to go through this in a little or the next slide, but this is what we can get from the equation, that the sum of the three forms of energy is constant. So energy is conserved, so it's very, very logical. And since the sum of the three is constant, we can rewrite the equation as or in another form, that for 2 points on the same streamline, the energy on one point is equal to the energy on the other point. This is the most common shape of the equation because we use it to get information about one point of the flow with the knowledge of information of another point of the flow. Bernoulli equation can be written in different forms. It can be written in units of energy or power. So it's PV plus mgz plus half mu squared is constant, which is the forms of energy that we are used to. It's the flow work, the potential energy, and the kinetic energy. We can divide the equation by mass flow rate. So it's going to be specific energy. So it's in this case, it's P over rho. Of course, mass flow rate is rho v. So if you divide PV over rho v, it's going to be P over rho plus Gz plus U square over 2 equals constant. And this is the shape that we got from the derivation. The equation can be divided by G, and it will have the units of length. And it's called head, and it's a common shape of the equation that we will use a lot later. So it's P over rho G plus Z plus U square over 2G is constant. Whatever shape that you prefer to use is fine. But just I wanted to give you this clarification that the three equations are the same. It's just how you express it in what units. One last thing to mention here about Bernoulli equation are the limitations. So we know already that there are some limitations like steady flow, that inviscid flow, it has to be an incompressible flow. There is no shaft work, which is one step in the derivation that we mentioned when we put the summation of forces at 0. There is no heat transfer, meaning that the density doesn't change, or to make sure that the density doesn't change, because density is highly dependent on temperature, and it has to be flow on a long streamline, meaning that the flow has to be continuous. So we need to make sure that these 3 points or these 6 limitations are already or the 6 conditions are satisfied when you use the equation. We will discuss how we can get around points 2 and 3, because these are important. There are cases that you cannot ignore the viscosity of the fluid. For example, if it's crude oil, it's a very, very viscous fluid. You cannot ignore the viscous forces. And if you have a pump or turbine, which is a very, very common case, you cannot ignore it at all. So in this case, we can use what we call a modified Bernoulli equation. We use the same equation, but we do some tweaks to the equation to make sure that it fits with these conditions. So this is what we will see at the end of this chapter, inshallah. But for now, this is what we need to know about Bernoulli equation. Next video, we'll have some solve some problems just to be more familiar with the equation. So I'll see you then, inshallah. Goodbye.